Okay, thank you very much for the introduction. So I'm going to present the work of a colleague of mine, David Gomez, who was not able to come today. This was a joint work between two teams in INRIAREN, the hybrid team and the mimetic team. So in this work, what we wanted to address is avatar interaction for, if it works. Okay, no. Okay, so in fact, for avatar interaction, what we consider is that so it's like the user is using the avatar as an interaction tool. So it's the way he has to interact with the environment. In this case, the avatar is the embodiment of the user in the. Okay, the avatar is the user embodiment in the environment. It can allow the user to interact with the object in the environment. Can also provide awareness in a collaborative virtual environment. So several users interacting in the same environment, they can use their own avatars to have a sense of identity, and also in some cases this can also provide some ownership effect, so like the more perceptual approach. Especially in this case, what we are considering is an avatar interaction in which the user is seeing his avatar. So we can consider it as a third-person view of the avatar. So the user is performing gestures, and the avatar is mimicking these gestures in order to perform the interaction. However, what we want to address is the mapping between the user and the avatar. Typically, for systems which using, for example, Kinect, the gestures of the avatar are directly mapped to the gestures of the user are directly mapped to the avatar, which in case that the avatar is performing, for example, a task which requires some effort, the user will not be able to understand what is the effort that the avatar is producing. So in this case, as the mapping is 1-1, the user has no information. So in this work, what we want to address is the enhance of this link. So in order to allow the user to perceive how the effort of the avatar. So in this case, so we want to simulate some effort with the avatar animation in order to enable the user to understand what is the effort that the avatar is delivering. In order to do so, what we are proposed to use is a Pseudo Haptic approach. In this case, the Pseudo Haptic is a technique meant to simulate haptic sensations, but using the fact that the visual dominance can sometimes overcome the haptic dominance, especially when the haptic is not present. And also, this is a feature that we want to enforce, so we don't want to use any haptic device, so the user will still be able to perform free movements. And the goal is how to alter this mapping between the user and the avatar to enable this perception. First, I want to just discuss a few works that has been done on pseudo haptics, which are relevant for this work. The first one is the work for Dominion et al. In 2005. In this case, what they explore is how to modify the perception of weight while interacting with a haptic device. In this case, what the user is doing is lifting an object which has a predefined weight. However, he is observing the movement of a virtual object which is controlled by his actions, and by altering the control display ratio between the action and the visual feedback, the authors are able to modify the perception of weight of the user. For example, if the virtual object is moving slower than the physical objects, it induces an increase of weight in the perception of the user. A second related work is the work for Push et al. In 2009. In which the user is able to see his body through a see-through head-mounted display, and the system modifies the displayed image of the user in order to induce some effects of a force field. For example, in this case, the hand the display of the hand is slightly moved towards one direction, which makes the user to perform a corrective movement in order to compensate for this effect, which provides a sensation of force. So the approach that we are presenting is what we call a pseudo haptic avatar. So it's an avatar enhanced with pseudo haptic feedback in order to modify the perception of the user. This approach is we address first the animation of the avatar. So we perform some motion capture data of our real weighting operations. In addition, we provide some real-time adaptation of these animations in order to induce the desired effect through the pseudo haptic approach. In this particular example, we are focusing on a single use case, which is a lift weighting operation. And in addition, we perform a formal evaluation in order to explore how our approach affected the user perception. First, I will talk a bit of detail about the components of our approach. So in a first phase, in an offline process, we perform a motion capture of the lifting operation. In this case, was lifting a dumbbell. After a motion reconstruction of the gesture and building a motion database of different lifting gestures. And in real time, the user is tracked using a single Kinect. And the avatar is interacting with a virtual object who has a predefined weight, and we use the information capture in the motion database plus the user interaction in order to adapt the animation in real time. First, I want to get a bit on detail about the motion capture of the motion capture. We use two different subjects for the motion capture, although we only consider one subject for the database. The task was simple, was lifting a dumbbell in pronation, which means that lifting the dumbbell in this position. We performed the capture of 4 different weights, 2, 6, 10 and 14 kilograms. So the user performed 12 trials with 3 repetitions, and we kept the animation which was better representing the gesture. A few details about the system and the reconstruction. We use a Vicon MX40 system with 12 HD cameras at 120 Hz. The user was wearing 27 reflective markers, which were reconstructed using Vicon IQ. And with this information, we were able to animate an avatar which had a skeleton similar as the Kinect. So now we only animated the upper body. So in fact, we only needed 9 joints. So regarding how the user is able to interact with the system, basically as we were tracking in real time the user, we mapped the position of the wrist in correlation with the animation of the avatar. In some sense, the screen acts as a virtual mirror. So the user is performing the gesture, while regarding how the avatar is also performing it. So the question here remained on how we could adapt the animation in order to enhance the perception of the user. We considered 3 different approaches. The first one is the speed profile, which was obtained thanks to the motion reconstruction. The second one is a simulation of the effort through the avatar posture. And finally, following a more classical pseudo-haptic approach by modifying the control display ratio, there is a typo there, between the avatar and the user. We go a bit on detail on the different 3 approaches. So the first one, which you call it a motion profile. Here the goal is to link the speed profile of the animation with the gesture or with the effort. So in this case, while analyzing the different different gestures recorded, we observe a different speed profile for each weight, which is expected. And the idea is to reproduce the animation recorded for a given weight. So when the user is lifting a virtual weight of 2 kilos, we play the animation of 2 kilos and successfully and subsequently. Here, we had a bit of work in order how to synchronize the recorded animations. Here we wanted to have almost a one-to-one mapping. However, the only changes is in the speed. For example, when the user was lifting a lightweight object, the animation is almost uniform, so the speed of the animation was almost uniform through all the lifting operation. However, when the user is lifting a heavier object, at the beginning of the gesture the animation is slower, which at the end speeds up. So in fact, the time of the animation is always the same for all the weights. There is only a change on the speed profile. But we just use the wrist position in order to, let's say, to determine the keyframe of the animation. Here is slide example. In this case, the animation is totally dependent on the user. So the user, the speed of the movement of the user really drives the animation. Here are two examples. In fact, in this approach was the one which delivered the less difference, which, as we will see afterwards in the evaluation. So the second approach was focusing on the posture of the avatar. In this case, we follow a simple approach which is based on changing the angle of inclination of the avatar. So here we want to link the lifting effort with the inclination. Here we just use a simple approach which modifies the spine inclination. So in fact, when the user has to lift a heavy object at the beginning, the avatar performs a forward inclination plus a backwards inclination at the end of the movement. In fact, this was computed through testing, so there was no specific law. In fact, at the beginning of the gesture, we perform a forward inclination, and at the end of the gesture, it's recovered. And if the weight is too heavy, it's even backwards. So this is how it likes. So this is as a lightweight gesture, so there is almost no inclination, and when there is a heavier weight, the inclination is increased. Sorry. Okay. Finally, the third approach, which focused on the control display ratio, altering the mapping between the user and the avatar. So in fact, here we play with the amplitude of the user movement. In general, in the other two approaches, the gesture was the amplitude of the movement was always the same. In this approach, what we want to do is exaggerate the gesture of the user. So in fact, when the user has to lift a heavier object, he has to exaggerate a lot the gesture in order to be able to lift the object. And this is mainly done by altering the control display ratio used for the first approach. So we have a scaling factor K, which determines the control display ratio, in which in the experiments range from 1 for the lighter object to 1.18, which correspond with the maximum amplitude of the movement of the user. So here are the two gestures at the same time. As you can see, in the light object, the animation is performed faster because the user needs to perform a lower amplitude movement in comparison with the second approach. Also, what is interesting about our approach is that all the different effects can be combined. Okay, so we can combine the motion profile, the inclination, plus the control display ratio. Okay, so once these are the three approaches that we were proposed. So the second step was the evaluation of these approaches in order to study the weight perception of the user for each one. In fact, the task was a weight discrimination task. The user has to sort 4 virtual dumbbells in the way that at the first step the users lift the 4 dumbbells and had to choose the one who had the heaviest weight. Then they had to do the same for the 3 remainings and then for the 2 remainings. And what they had to do is always observe the avatar while performing the lifting operation. So 11 participants take part on the experiment, 5 females and 6 males. Here is how it looks the experimental setup. The user interacts with a 50-inch monoscopic display with a Microsoft Kinect for the tracking, and he had an interaction prop which was a wooden stick, almost of 200 grams, so not heavy at all. Regarding the independent variables, we had 7 different levels of visual feedback. 3 for the feedback alone, so the motion profile, the angle of inclination, and control display ratio, and the other 4 combinations between all these feedbacks. Regarding the weight of the dumbbells, there are 4 different levels, so 2 kilos, 6 kilos, 10 kilos, and 14 kilos, which match the motion capture we used. And for the ordering, we use a simple Latin square design with 7 repetitions for each visual feedback, which in total represented almost 450 lifting gestures of the user, and the experiment lasted around 40 minutes. And regarding the measure we recorded, we considered the ordering time, so how much time the user needed to perform the task, plus the ordering error, which in this case we used a squared error for determining the error. And our hypothesis for these experiments is that when combining several visual feedbacks, the recognition rate will increase, so users will have a better perception of the virtual height. And we were expecting no differences neither on the ordering error or the ordering time for each approach. So first I will discuss the ordering error. In fact, there was a strong main effect for its visual feedback, and this inhabilitates the first hypothesis because there was a strong difference between all of the three different visual feedback provided. In fact, the one who better worked was the console display ratio, followed by the angle of inclination and the motion profile. All three were significant difference. And in fact, what we see is that for the motion profile, almost the result was random. So users weren't really knowing what they were doing. In fact, some of the users said that they perceived during this condition that there was latency in the system, as sometimes as the movement was delayed due to the weight of the object, the users linked the latency, so they thought that there was an issue with the system. Also, a strange effect that we still don't know what happened is that when we combine the angle of inclination with the motion profile, the recognition rates decreased a lot. So that was still an unexpected result. And also what we observed is that while merging the different visual feedbacks, when the visual feedback considers the console display ratio, more or less there was no difference between the recognition rate. So in fact, from the console display ratio plus all the other combinations, there were no significant differences. So considering our hypothesis, we had to reject the first hypothesis and also the second one, as we were clearly a difference in recognition for all the three different visual feedbacks. Regarding the ordering time, although there was some main effect, the differences were pretty low. In fact, the mean ordering time was around 30 seconds, and the deviation was not that high. So even and in fact, for the three visual feedbacks alone, there were no significant differences. The only significant difference was with the combination of the three visual feedbacks plus the angle of inclination. But the differences, as you can see, are really low. So a few words on the user preferences. Most of the users were split between the console display ratio and the angle of inclination. As you might imagine, for the results, no user preferred the motion profile, as it was perceived as a latency, as an issue of the system, rather than a feature. And also the users prefer the combination of different visual feedbacks, as it makes more evident that the difference between the weights of the objects. Okay, so in order to conclude, so in this work we have proposed a new concept, which is a pseudo haptic avatar. What we want to do with this work is to physicalize the avatar-based interaction. So the user, when he's interacting with the environment through an avatar, we want the user to obtain more information of the system or of the virtual environment without the need of haptic devices which might interfere in his interaction. And also we have proposed three different effects: the temporal, which with the motion profile, the postural with the angle of inclination, and the spatial with the console display ratio. And from all the three effects, the one which we will keep on studying would be the spatial one, which is the one which provided a better recognition and which also it's simpler. However, with the postural, it could be interesting to explore how additional changes in the additional procedural changes on the avatar might increase the perception of the user. In this case, what we want to avoid is to have to perform motion capture data for a lot of wide range of tasks and gestures and weights, which will increase a lot the development time of an application. Okay. So, and also for future work, what we want to do is to extend this concept to other interaction tasks and also explore the limits of the user perception. So, which is the just noticeable differences between that the user can perceive. So, we provide two different weights, up to which extent the user is able to recognize that both are different. And also in terms of application, the main application we envision is to use it in sport simulation in order to simulate, for example, context or simulation that are hard to perform in procedurally. For example, also for training complex motor tasks. Okay, I think I'm on time, so this is the end of my presentation. Thank you very much. This was the last one, so thank you for being there.
Hi, Regis Kapper, Duke University. Great work. I think that's really nice.
Thank you.
I have a couple questions. First, have you considered using an immersive system, especially for getting rid of the real body, in terms of the prop? And do you think that would have had any difference?
Yeah, in fact, this is something that I would really like to explore. So, what happens when you are with a head-mounted display, for example, and you really see the virtual object in front of you, and you introduce a mismatch between the real avatar and your movement, because in this case was kind of evident because the user is able to see both his body and the avatar.
Right.
Although we enforce them to look at the but in proprioception is a strong effect. But in this case, I think it would be really interesting to see up to which extent in an immersive environment, which the body is substituted with a virtual avatar can. Which are the limits we can really simulate.
Right. The other question that I have is with regards to the, especially I think with the control display ratio technique, we typically for controlled movements, we exert force. So one way that, and this is probably more of a comment than a question, it might be interesting to use EMG or something like that as an objective measure of perceived force rather than just subjective ratings.
In fact, this would be interesting because in this case, so if while performing these studies, we observed that the visual feedback is able to change how the users really exert his muscles, it can be really interesting. Yeah. I think there's been some work in which they explore the excess of exertion while performing lifting dumbbells, how the visual feedback might change the level of exertion. That this can be really interesting for validate the approach.
Right.
Yeah, absolutely.
I have a question. I understand why you didn't do it in this study, but there's this really well-known visual illusion, right? Size-weight illusion, that things that are bigger appear heavier. And I wonder if you're planning on sort of seeing how that interacts with this animation, right? Simply making the dumbbells bigger. And one side effect of that is something that I think would be awesome, is just to make people feel like they're superhuman, right? They can pick up super large things. And so I wanted to know what you thought of that.
The thing is that you have to be, so the avatar can behave like a superhuman, but the user has to feel that he's also superhuman.
Yeah, sure.
No, because you need to have if you really have the connection with the avatar, or you have a good embodiment with the avatar, maybe you will feel that maybe you are superhuman.
So the animation is important, but the size of the object is probably, I mean, you kept the size constant, obviously, because you want to look at the animation, but have you thought about, if it's really pseudo haptics and to your argument of visual dominance?
Yeah, in fact, I think it's an approach that can be easily combined.
Yeah, great. So. Okay, so I think if there's no more questions, we want to thank all of our speakers again.